All right, everybody. This is Carol Madden at HORIBA Scientific, and I'd like to introduce Dr. Jeff Bodycomb, who's going to be talking about green goals with Zeta Potential.
Yes. Well, welcome everybody again. Once again, I'll put in a last plug for PitCon, booth 1039. And then moving on to talking about meeting green goals with Zeta Potential and the SZ100. And some of you notice I like plays on words, and really using Zeta Potential can help you save money. And that's one green goal, because money, at least in the US, is green. And the other is you can use Zeta Potential to improve your environmental performance, and that is another green goal. And I'm going to talk today about wastewater. So if you've heard me before, I've talked about Zeta Potential and formulation work. Here, we are working at the other end, where we're trying to take formulations apart, if you will. So you have wastewater that contains some sort of particulate contaminants that need to be removed for safety, environmental, or aesthetic reasons. So for example, if you have drinking water and it's cloudy, and the cloudiness is from something completely benign, it still looks kind of yucky. And so, of course, if the cloudiness is like milk and it's from milk fat and protein, that looks great, but that's a different matter. Here we're trying to remove these contaminants so it looks nice, so that it's better for the environment and more safe. Zeta Potential is a particle analysis technique. It can also be used to characterize charge on polymers, but really discussion today is about particulate waste. If you have dissolved metals, dissolved heavy metals, probably a lot less useful to you. Well, how do we look at particle contamination? And so let's talk about haze, which is something that is relatively routine to measure and can tell you, hey, you have some reasonably large particulate contaminants. You can look at total suspended solids, where you filter and weigh the wastewater, or you can look at scatter intensity with a turbidity meter. And EPA has a method, and HORIBA actually manufactures the U53 for these sorts of measurements. And you can kind of see a picture of that. It's a handheld meter on this right-hand side of the slide. Well, now that we know we have particles, how do we get rid of them? Well, if you have particles, you'll notice that they tend to sink or float. So you can put the particle into a giant tank and wait for them to sink to the bottom, and you have a sludge at the bottom, or float to the top as a cream. So the way I've drawn this here, I have particle-free water on top and sludge on the bottom. If you look at the bottom of this slide, you can see various geometries for settling tanks. Now, where basically you flow water in, you have a tank big enough that it sits there for a good long time, and the particles come out. Well, that's easy enough, and you can actually build one of these tanks without ever saying the word Zeta Potential. Now, there is a desired settling process, which is a little bit more complicated than what I just said, which is you start with some sort of suspension of particles on the left. And you want to flocculate the particles so they become bigger flocks or clumps, and these bigger flocks or clumps will tend to settle. Now, why do we want them to be bigger? Well, we can look at Stokes' law and look at settling velocity, which actually increases with the square of particle size. If you double your particle size, the particles settle 4 times faster. So here's the equation. Velocity is twice the density difference times gravity times r squared divided by 9 times viscosity. Really, if you look on the top, that's your gravitational force, which is going to increase with particle volume, or r cubed. And your viscous drag on the bottom will only increase with particle radius as a linear term. And so you ratio those two, you find that r squared term. So your settling velocity increases with r squared. So larger particles means faster settling, which means you use a smaller tank, and that makes for a less expensive process. So how much does it matter? Well, here's a nice table using the equation before, where I have diameter on the left, kind of an order of magnitude for the size to give you a feel of what's going on, and the time for the material to settle 1 meter. And I have a density of 2.6 like you have sand, density 1.3, specific gravity, I apologize for that, which is like clay. So density would be 2,600 kilograms per cubic meter, or 1,300 kilograms per cubic meter. So a 1 millimeter particle, which is about as big as sand, is going to settle in about a second to 6 seconds. If you have everything stable in Stokes, and we're going to leave aside whether that's right for such a large particle. But where this is going is you're not really going to worry about that kind of settling process. At 1 to 6 seconds, you're more worried about the stuff settling your pipes, unless you run your pumps. As I move my diameter down to 100 microns, which is like fine sand, well, now we're looking at 100 to 600 seconds. So that's about 10 minutes. Doesn't sound too awful yet. 10 micron, which is about the size of silt. Well, now it's 3 hours if it's something as dense as sand, or 17 hours if it's something like clay. This is getting to be a while. If I go to 1 micron, which is the size of the bacteria, it's 13 days or 70 days. And of course, if you're actually using bacteria, which are mostly water, and the density difference is small, that settling time is really, really long. And then as we move down to colloidal particles at 100 nanometers, 0.1 micron, we're waiting 3 to 20 years. And most people don't really want to wait that long or have a tank with a residence time of 20 years. It's just, looks like the ocean. So as you get to these smaller particles, this settling time gets really long, and that gets to be really expensive. So we want to make our small particles large. So people have been doing this for a while. They start adding things like coagulants, and there's references that go way, way back on using different additives to help clarify water by acting as coagulants. A couple of popular ones, or I mentioned 3, would be something like alum, aluminum sulfate, ferric chloride, or if you want to get fancy, and these are really effective, or we use things like acrylamide, acrylate copolymers, because you have carboxylate groups, and so these are anionic. Now notice, and you can also do cationic polymers. I should have picked a cationic. Man, I labeled my slide wrong, sorry. You should have picked a cationic polymer for the example. So aluminum, okay, so and what's in common with all these are multivalent ions, okay? So you have multiple plus charges or multiple minus charges. You'll see why that's important soon. So I want particles to flocculate. I mentioned these magic materials, and to tell you why they're important, I'm going to mention what's going on. Well, fine particles will like to flocculate to reduce surface energy. So I have 2 particles, and they touch. Well, you can see that this total surface has gone down. So that's a reduction in surface energy. So once they touch, they will like to stay together. And that's a good thing. Unfortunately, many particles in aqueous suspension, or unfortunately in the case of water treatment, have a surface charge and therefore repel each other. They never touch. Now, formulation scientists will go through life trying to find strategies to keep particles from touching so that the colloidal suspension stays suspended. Here we're doing the opposite. So if you have particles with a strong negative charge, they're going to repel each other. So I have a particle here that's negative, a particle here that's negative. They're going to repel, they're not going to touch, or they're very unlikely to touch. And so you have a kinetically stable system. So we don't like that. We want to neutralize the charge. And so we're going to neutralize these negative charges with, say, polycations. How do we decide which polycations to use and how much to add? Well, the one classic method is a jar test. You fill identical beakers with identical amounts of your waste. You keep one kind of as a control, and you add varying amounts of coagulant and evaluate the results. Do you see your very fine particles start to clump up into visible flocks? That's a good idea. If you're patient enough, you can even wait and see how long it takes for the particles to settle. It's inexpensive, so that's always a great feature. You basically need a bunch of beakers, a bunch of stirrers, and a light box. And then it's operator dependent. You're really counting on your operator taking having the time to sit and look at these suspensions and evaluate each one. And if you have the same person every day, that's good, as long as they always come in the same condition. If they have a cold one day, or and they don't make it to work, your results could shift. And it can be a time-consuming measurement. So now we're going to invoke the concept of zeta potential. So rather than have these magic chemicals that we add and we look at what's going on, we're going to look at the mechanisms. So zeta potential is a charge on a particle with a shear plane. So you have a charged up particle here, a bunch of negative charges, and then it's going to move through life or through the liquid, carrying some liquid with it. So we're going to have an imaginary plane, the shear plane, which is going to be the particle and everything that moves with it. And you have the bulk liquid out here. And we're going to look at the charge right at this dashed line and use that to think about what's happening in a colloidal suspension. So if I can turn off that charge, the particles will flocculate, more rapidly settle, or be more easily filtered. And that's a process I haven't talked about, but it's also, as you can imagine, it's easier to filter big particles than small ones. So we can use multivalent ions, calcium, aluminum, iron, or polyelectrolytes, acrylamide, acrylic acid copolymers. So here I have a negatively charged particle, and I start adding aluminum into the system, and the aluminum will start to bind to the particle surface because it's very cationic, so it likes the negatively charged particle, and eventually neutralize the charge in the particle. So now these particles will randomly bump into each other. There's nothing keeping them apart, and they'll start saying, hey, I have a reduced surface. Let's stick together, form a large flock, and settle out more quickly. So where does that happen? Well, this is a good time to introduce the concept of an isoelectric point, or IEP. On the left, I plot zeta potential, which is the surface charge. And on the bottom here, I plot pH, and I'll show some other plots where I'm going to use calcium or other ion concentrations. I'm going to say, hey, at low pHs, where I have lots of hydrogen cations, I'm going to have a positively charged particle. As I increase the pH, the particle charge will move to zero and eventually become negative. Now, of course, this depends on the surface groups on the particle. And so for different materials that you measure, you will get different answers. And some materials will always have a negative surface charge because they just aren't that sensitive to pH. But they could be sensitive to something else. So the isoelectric point is the point at which the zeta potential or surface charge is zero. So I can add potential forming ions and add charge modifying agents, coagulants and flocculants mentioned earlier. So this is really, we need to know where to find the isoelectric point because that's going to tell us how to control the system. So I mentioned this imaginary plane and measuring the charge of the imaginary plane, and I mentioned what to do with the information. So how do you make the measurement? Well, there are a few techniques. One set are the acoustic techniques where you use sound to probe particle response. One older method is to use a microscope where you actually look at the particles, and if they're big enough, you can see them under a microscope and watch how they move. It depends a decent amount on operative skill and does not look at very many particles. But the most popular method these days is to use light scattering to look at the motion of the particles due to an applied electric field. So this is known as electrophoretic light scattering, and more commonly talked about as zeta potential measurement. And so we can use that to find electrophoretic mobility and zeta potential to teach us about charge effects in our colloidal system. The HORIBA SC100 is one instrument for making the measurement. Actually, can also be used to determine particle size and polymer molecular weights. What happens inside the instrument is that you have a cell and with some suspension, that's in blue, and a positive dark blue electrode and a negative pink electrode and gray particles, and I apply an electric field. The incoming light is scattered off the particles and has a Doppler shift due to the particle motion with respect to the fixed electrodes. So all the particles are swimming to the left, so I pick off the scattering over here on the diagonal, and if I look at the frequency shift and scattered light, that will tell me about the particle motion. From particle motion, as a function of the field strength, I can get electrophoretic mobility, and then from electrophoretic mobility, I can get zeta potential. And then from a series of zeta potential measurements, I can find out how to manipulate the charge on my system, and in this case, figure out how to get the charge to zero, spending the least amount of money, and making the cleanest water possible. Let me give you an example of what I mean by surface effects. So here I have different grades of TiO2. I plot mobility on the left, which is proportional to zeta potential. And you can see these curves, and you'll see that depending on what's on the surface, so this is the same bulk material, TiO2, and you get very different behavior. So the silica surface materials, which will be like R931, will have an IEP that's acidic, R960, also slightly acidic. But if you go to R900, these are DuPont grades, I think, then the material we tested went basic. Now, very nice, clean, pure materials. What's really happening is that different surface impurities are affecting the results for zeta potential. And what's important in this in wastewater is that as your process shifts, or the process creating your waste particles shift, you're going to get different results for isoelectric points, not just as a function of pH, but also as a function of coagulant dose. So let's take some clay. And then this is a sample that it was a clay. They wanted to get all the clay out of the system. Now the big chunks you don't care about because they're big. They're going to settle anyway. It's the fine ones that you measure by light scattering that are the ones that give you the most trouble. It's the most surface in the system. They're the ones that you really want to flocculate nicely. So I made measurements of zeta potential on the left as a function of pH. And you can see that when I started at pH 6, quite negative zeta potential, very nicely suspended material. And then as I lowered the pH, I was getting zeta potentials that were climbing towards zero, which is what you expect. Now, in this case, we want to get rid of the clay. And so, whoops, sorry about that. Once the pH got to about pH 2, we said, you know what, this is really going to take up a lot of acid. Not as much fun as everybody wants. So before we move into what the next step, I'll mention that you can make these measurements with a auto titrator assembly and have a system that automatically doses acid and bases to adjust pH, and then connect that to the SC100 instrument. So the overall system kind of looks like this. If pH does work for you, and by the way, if you're using something like alum or ferric chloride, you're going to also worry about pH. You will want to start controlling that in real time. And we're HORIBA. We have friends and other groups in the company, and you can use things like our pH controllers to manage this process. So let's go back to the clay. So after I talked about pH and said for this particular material it didn't work that well, let's plot zeta potential as a function of gypsum. So this is calcium plus 2, and then milligrams of reagent per milligram clay. And notice I use a log scale on the bottom. So just like pH, I like a log scale here because I need to make fairly large changes in additive concentration. And you can see that as I add gypsum, the zeta potential is climbing up towards 0. But it doesn't quite get there, and I'm at 100 milligrams of reagent per milligram of clay. So I pretty much know that gypsum is not going to do the job because I'll have a gypsum slurry by the time I'm done. Let's do something trivalent alum. This is a potassium aluminum sulfate. I mentioned before the aluminum sulfate pure, but this is the stuff I have potassium aluminum sulfate here, so that's what we used. You notice that the blue with the alum is shifted far to the left. So as I start adding the alum to the clay, it has a very strong effect, and even a tiny amount of trivalent aluminum gets the zeta potential up to 0. There's another effect here, which is as you add more and more, the surface charge goes from 0, so it starts negative, goes to 0, and then becomes positive. Well, that's not good news, because once you drive the surface charge positive, the particles will once again repel each other, and once again you will restabilize your suspension. So adding the right dose is really important, because if you add too much, you're not just wasting money, you could be wrecking your process. What about oily waste or oil and water? Things you can measure, there are Oakland 350, or doing hexane extraction, which is fairly slow, EPA method 1664. So I could take some oily waste and plot zeta potential as a function of coagulant, and this is parts per million coagulant solid, so really it's the mass of coagulant versus the mass of dirty water suspension. And there are two things. One is we're really adding a tiny, tiny amount of coagulant. The second is this is a proprietary formulation. I'm pretty sure it was a polycation, but they didn't really tell us anything, and so that's all we know. So you don't need to know much about the coagulant you're using to make these measurements. The second thing is, as I add it, I only need a little bit, that's great, but if I add too much, I can restabilize the suspension. And so once again, that's going to drive home the importance of making these sorts of measurements rather than simply saying, 2 ppm works well, let's go up to 20 just to make sure things work. No, you're probably not going to help you at all. So I made a quick comment in the beginning that we can't analyze non-particulate waste with zeta potential, but we do have fluorometers that will do things like measure color dissolved organic matter, and so in our fluorescence group, like the Aqualog. So a couple quick conclusions. Zeta potential really gives you a tool for understanding what different treatment options are doing to the particles. So you can really take apart your waste suspension and monitor what's going on. And this understanding is really necessary for optimizing your water treatment process, not just in terms of cost, but also in terms of how long the process takes and not breaking the process by restabilizing a suspension. So now I'm going to stop for questions and answers. You can read our monthly newsletter or visit our download center at www.horiba.com. Email us at labinfo@horiba.com, or you can just email me if you have questions. And then here I will turn the floor over for questions.